have a look at worksheet number 7. Specifically, we're going to look at question 2A and question 4. There's two different kinds of questions on this worksheet. There's one-dimensional, 3-charge problems, and then there's two-dimensional, 3-charge problems. So we'll take a look at one of each. Again, specifically 2A and question number 4. 2A says 3 charges are in a straight row. The first charge has a value of 2.5 times 10 to the minus 2. Let's label that. The second charge is to the right of the first charge. Okay, it has a charge of negative 4.00 times 10 to the minus 2. And the third one is to the right of the second one, and it's going to be 3.00 times 10 to the minus 2 coulombs. Let's label the distances here. We got 60.0 millimeters, and then we have 5.00 centimeters. We've got to be careful here of a couple of things. One, these are non-standard units for distance, but two, they're different units for distance. We got millimeters and centimeters in the same question. We've got to end up converting both of those. Okay, let's do our free body diagram. The net force on the first charge. Well, the force caused by number 2 is to the right, because number 1 and 2 are opposite charges. They're going to attract each other, and when they attract each other, 1 will be pulled to the right, 2 will be pulled to the left, but I don't really care what happens to number 2. So I'm just focusing on the force on number 1, the force of 2 on number 1. Now, what about 3 and 1? They're like charges, so they're going to repel. That means 3 is going to be pushed away from number 1 to the right. 1 is going to be pushed away from number 3 to the left. We'll call that F31. We can calculate both of those forces. F21 is KQ1 Q2 over R squared. R, though, well, be careful here. R is what? 60 millimeters divided by 1,000 is 0.060 meters. And then, of course, you've got to square that. When you solve for F21, you end up getting 2.4972 times 10 to the 9 newtons. Then we're going to solve for F31, which is KQ1 Q3 over R squared. Careful with R, especially careful with R this time. What's R going to be this time? 0.06 meters plus 0.05 meters. So you can divide the 60 by 1,000, divide the 5 by 100, because it's in centimeters already. 0.11 meters. And again, don't forget to square that. You do the math there, and that works out to be 5.5723 times 10 to the 8. Now, combine them. How do you combine them? F net, right? Just like in physics 20, F net is equal to the sum of those forces. F21 plus F31 in this case. F21 is a negative value. Hold on for a second. F21 is a positive value. Positive 2.4972 times 10 to the 9. And F31 is a negative value. It's 5.5723 times 10 to the 8. We add those up, and we get a value of 1.94 times 10 to the 9. Get a positive value, which means it's acting which way? To the right. All right, good? Odds are we're going to see one of these on our exam. Okay, there's a very, very good chance we will. It seems like every year they put one of these three-charge, one-dimensional problems on our exam. Now, we often see one like this too, right, Carly? Question number 4, which says repeat question 2B, not repeat question 2, but repeat question 2B, only 2B, so we don't have to repeat everything. Okay, question 2B has 3 charges, but we're going to this time make the first charge above the second charge. This is going to be 1, this is going to be 2, this is going to be 3. Nope, that's not right. Yeah, that's right, yeah. This is 2.50 times 10 to the negative 2 coulombs. This one is negative 4.00 times 10 to the negative 2 coulombs. And this one is 3.00 times 10 to the negative 2 coulombs. Same data, except the placement of charge 1 is different. Same distances, 60.0 millimeters and 5.00 centimeters. What's the force on charge 2? Well, 1 pulls 2 upward. Okay, 2 is attracted to 1, 1 is attracted to 2. But I care what happens to number 2. If it's attracted to 1, it's pulled upwards towards number 1. The force of 3 on 2 is to the right because it is also an attractive force. Positive and negative attract each other. 2 gets pulled to the right towards number 3. 3 gets pulled to the left. Now we calculate these forces, which you'll have already done in a previous question. F12 works out to be, wait a second here. Yeah, no, that's right. F12 is 2.4972 times 10 to the 9. And F32, the value of that one is 4.3152 times 10 to the 9 newtons. Then we combine them. We say this is 4.3152 times 10 to the 9. This one is 2.4972 times 10 to the 9. And our resultant vector right here is our net force. So how do we find F there? Now it's easy. Now this is like grade 9 math now, right? Yeah, it's the Pythagorean Theorem. It's the square root of this squared plus this squared. Okay, when we do that, F works out to be, the magnitude at least, works out to be 4.99 times 10 to the 9 newtons. And where am I going to put the angle there? Where am I going to put the angle, Daniel? Let's say position 1, 2, or 3. 3, always at the start of that diagram. Again, it's a lot easier to see that when we have our arrows drawn. Okay, if we don't draw our arrows, then it's, well, you got a 50-50 chance of putting it in the right place. Theta is the inverse tan of opposite over adjacent, which in this case is 2.4972 over 4.3152. Well, there's 10 to the 9 in there, right? Do I need the 10 to the 9 in there? No, I don't here, actually. Why was I able to drop the 10 to the 9? Sorry? Yeah, if you have 10 to the 9 on the top and 10 to the 9 on the bottom, you can cancel out the 10 to the 9, right? It just makes my life a little bit easier punching it into my calculator, that's all. Do the math, works out to be the same answer either way. Theta is 30.1 degrees. Now, when I expressed that on the answer sheet a few minutes ago to you, it said north of east. Remember we said yesterday, though, we don't want to use north of east here? So we should just leave it at that. We don't want to use north of east here because our frame of reference is not defined for us as north, south, east, west. So just leave the angle labeled on the diagram. Good? Feel okay about that? Okay, let's do one more question. This one's going to be a challenge question. I want to do what I call my C20, Concept 20, special, wow, these are hard examples that you should not lose, bonus questions. There's 4 of them. Okay, there's a couple of them that are not so bad, but there's a couple of them that are pretty challenging here, actually. Here's the scenario. We have this situation where 2 identical conducting balls, B1 and B2, each of mass 25 grams, are hanging on a 50 centimeter long insulated threads. They become equally charged, although it doesn't really matter if they're equally charged. Okay, they're going to end up in the same place, whether they're equally charged or not, right? Because the force acting on A will always be equal and opposite to the force acting on B. If the forces are the same, then how much charge is on each one is irrelevant in terms of which one's deflected more, right? They'll both be deflected the same. They become equally charged and come to rest with angles of deviation 45 degrees from the vertical. If they're at rest, if they come to rest, and then that basically means that they're in equilibrium, right? They're in equilibrium. The forces are balanced. The net force is 0. that make sense? All right, let's move on and see what they're asking me here. It says the electrostatic force between the charged balls can best be described as what? Is it attractive or repulsive? It's repulsive. We know it's repulsive because they're not coming together, they're spreading apart. It's repulsive due to similar or dissimilar? Similar charges, right? We usually talk about like charges as opposed to similar charges, but you can distinguish between those two words, right? Similar versus dissimilar, like charges versus unlike charges, or opposite charges. The answer for number 1 is D. That's a relatively straightforward one. Now, question number 2, I boxed this one off because this is the real challenge question here. What is the tension in a thread supporting one of these balls? I remember this, I don't remember if it was this question, but a question like this appeared probably 15 years or so ago, maybe even more than that now. And I remember when it appeared for the first time, I remember thinking like, wow, that is not going to be a well done question. That is a hard question. And sure enough, it was not well done by anybody in the province, including people at this school. But since that time, they've put maybe a half a dozen times on the exam questions similar to this one. And of course, they're still not particularly well done, but they're better done than they were that first time. I don't think that's a fair question to ask you the first time on an exam. I just think it's too crazy. But if we go over something like this, if they happen to ask you something like that again, then it's fair game, right? We want to find the tension in one of these strings. Okay, I'll tell you, the first time that I saw this, I thought, the only thing that I could think of right away was, oh, well, the electric force is kq1 q2 over r squared. Maybe I can get the tension somehow from the electric force, right? But then I realized I didn't know what q was. I don't know what q1 or q2 is. I didn't know what r is, the distance separating them either. So that kind of fell apart. I wasn't sure what to do. But the difference between you and me, between some of you and me, is not our level of intelligence. Okay, you guys are smart. I'm smart. You're smart. We're all smart. Yeah, I might know more than you, but some of you guys are as smart as I am. Some of you guys are probably more smart. See, there you go. I didn't even smarter than I am. Those of you who knew that more smart wasn't the right way to say it are probably smarter than I am, right? But the difference between you and me is that when I see something like this that I'm not sure what to do with, I'm not afraid to try it. Like, I'm confident that I'm going to get it, even when I'm not sure what to do. Started trying things, and the only thing that I could end up doing, and this wasn't because I knew this was going to lead me in the right place, is just, I'm trying it, right? See what happens. I thought, well, try drawing a free body diagram. I know the force of gravity acts down. I know that the electric force has to act this way because it opposes each other, right? And I know that the tension has to act this way. And that's what it came to me. I realized, not because it didn't come to me, or I didn't do this because it came to me and I knew what to do. It came to me because I did this, and the light bulb turned on. The force of gravity is mass times 9.81, so 0.025 kilograms. 0.025 kilograms times 9.81, and when I multiply those two together, I end up getting 24525 newtons. And I recognize that if the forces are balanced here, if it's in equilibrium, if everything's suspended, then the y component of this tension has to equal the same value. Does that make sense? If it's not going up or down, the up and down forces have to balance. Similarly, if it's not going left or right, the electric force has to balance with the x component of the tension. Make sense? Well, I know the angle here is 45 degrees. So if I know the angle and I know the adjacent side, I'm looking for the hypotenuse, why don't I just find the tension by saying cos 45 degrees is equal to adjacent over the hypotenuse. Ft is equal to 0.24525 divided by cosine 45. And when I do that math, it works out to be C 0.347. Oops, guess that's on the next page. Does that make sense? Now, over the years, hold on, we're not done yet. Over the years, I've seen some questions that have been slightly different, but really similar to this. Okay, maybe I could ask you for the electric force instead. What would I do for the electric force? I just use tan, that's all, right? I'd say tan 45 degrees is equal to Fe over the opposite side over the adjacent side, and I'd find Fe just as easily as I found the tension there, right? Now, conceivably, maybe you're given one of these forces, Ft or Fe, and you're asked to solve for the gravity and therefore the mass of the object, right? But ultimately, whatever you're asked for here, it boils down to the same thing. Now, number three says if the charge on B1 is tripled and the charge on B2 is reduced to 1/3 of the original amount, what's going to happen to the angle of deviation? Well, if one charge is tripled, one charge is cut in by a factor of 3, then the force is going to remain the same, right? If the force remains the same, what's going to happen to the angle? It's going to stay the same. It doesn't matter that one has more charge than the other. The force acting on one is equal and opposite to the force acting on two. The forces are the same. And just because we cut one by a factor of 3 and increase one by a factor of 3, okay, the force remains what it was, the angle of deviation will remain what it was. And finally, number 4 says if the electric force between the particles was 9, move together till they're 6 centimeters apart, the force between them becomes, well, the original force is kq1 q2 over r squared. I'm going to say my new force is kq1 q2 over, what would I say here? Over what? 2/3 r. What do I do with that? Square it, right. So it becomes kq1 q2 over 4/9 r squared, which is 9 over 4 times the original force there. So the answer for that one is going to be D.